10, come on. Everything's kind of slow today. I'm just trying to pin my video. It doesn't seem to want to respond very quickly. There it is. Okay. So again, we have just any old linear function. It can always be expressed in a way that you should by now understand quite well as a stretch and a shift of the y equals x function. We have our basic exponential function. Okay, so we have a linear function and an exponential function. So I'm going to make the standard table. For the exponential function and a table, and I'll just use the same values. Now we wouldn't ordinarily make a table with 5 values for a linear function because we only need a slope and a slope and a y-intercept or any intercept, slope at any point, or the 2 intercepts. Many ways to graph, but we only need 2 points and we only need the basic linear function and knowing what the stretch and shift is to construct the graph. So we would not ordinarily construct the graph this way. But, okay, we get -9, -7, -5, -3, -1. Okay, now let's look at these tables. If I just gave you these 2 tables, you might well recognize this one as your table for the basic exponential function, but you wouldn't necessarily recognize this one. Now, hopefully you would see, if you just look at these numbers, that these numbers just change by 1. Okay, -2, add 1, you get this, add 1, you get this. So these numbers change at regular intervals, the x values. The y values also change by the same amount every time. Okay, you add 2 to -9, you get -7. You add 2 to -7, you get -5. Add 2 to that, you get -3. Add 2 to this, you get -1. So you can immediately see that this is a linear function. Now, if you don't immediately see that, it's kind of okay because I'm going to give you a method for seeing it. Why do these change by 2? Well, it's because of the 2x. If x changes by 1, 2x is going to change by 2. That's a vertical stretch, if you want to think of it that way. And you get all this. So you should understand as much of that as you possibly can. But the way I'm going to analyze this now shows you a formal way you can do this, no matter how nasty these numbers are or how nasty these numbers are. A formal way that you can identify linear or exponential functions. Having said that, it's not particularly useful for real world data. There are other ways we do it, but we want to understand this anyway. The reason is these numbers have to change at regular intervals in order for this to work. Okay, so x changes by the same amount every time. X always changes by 1 as we go down the table, either this table or this table. So the y values form a sequence -9, -7, -5, -3, 1. Well, to get from -9 to -7, we have to add 2. From -7 to -5, we have to add 2. Here we have to add 2. Here we have to add 2. Okay. Same change in y. Every time. Not a formal way of stating it, but good enough to understand the pattern. That's always the case for linear function. If your x values always change by the same amount, your y values will always change by the same amount. That amount is incidentally the slope times whatever your change in x values is, but don't worry too much about that. Apparently can't spell. That's even worse, but okay. Okay, over here. Y values are 1/4, 1/2, 1, 2, and 4. They don't change by the same amount. To get from 1/4 to 1/2, you got to add 1/2. To get from 1/2 to 1, you've got to add, I'm sorry, add 1/2. You add 1/4. From 1/2 to 1, you add 1/2. From 1 to 2, you add 1. From 2 to 4, you add 2. Now, coincidentally, for this particular function, these numbers just mimic these numbers. That won't always be the case, but these are not all the same. Okay? These are different. So this function is not linear. Now, we already know that this function isn't linear, doesn't make a straight line. We know perfectly well what it does, but just using this as an example, no matter what the values are here, if the changes are not all the same, provided your x values all change by the same amount, if these don't all change by the same amount, it's not linear. If they do, it is linear. Okay. So that doesn't mean it's exponential. We could have done the graph of y equals x squared, and the numbers wouldn't have all been the same. Okay. Other characteristics of a quadratic graph that we'll talk about later. But the point is that there are many functions that aren't linear. How do we know that this is exponential? Okay, so why is it exponential? Well, because it's our basic exponential function, but let's pretend we don't know that. Let's come up with a test for exponentialness, okay, which is not a word. Why is this exponential? Well, let's look again. If we take 1/2 and divide it by 1/4, this equals 1/2 times 4/1, which equals 2. So looking at ratios of these numbers, which is just the ratio is one number divided by the one before it, okay? The ratio is 2. Well, 1 divided by 1/2 equals 1 times 2/1, which equals 2. The ratio here is 2. Here we have, I'll write it a little lower, 2 divided by 1 equals 2. So the ratio here is 2. And clearly the ratio here is going to be 2 because 4 divided by 2, we know perfectly well, is 2. Now you got to be able to divide fractions. And this is something that's such a challenge to students who come out of our universal curriculum in this country. We put calculators in people's hands and they forget how to do anything except use the calculator, often inappropriately, which is why one of my classes is all failing. It's one of my more advanced classes with students who should know better. They don't. It's not their fault, but it's their responsibility if they want to continue with their intended career. So I don't know what they're going to do. Waiting for response to my last email. Okay, so anyhow, people don't know this. You need to know it. There's a good chance you're going to need it again. Okay, so 2 things. 1, make sure you know how to do fractions. 2, your test for linearity is the change in the number is always the same. Your test for exponential is the ratios are always the same. So test for linear is a uniform change. Test for exponential is a uniform ratio. Okay, now none of this depends on any of the stuff you did in chapter 2 or chapter 3. Okay, doesn't depend on much of anything except your ability to do arithmetic and to know the basic functions. Okay, so we're starting kind of new here. This chapter, no matter how well or how poorly you've done previously, or whether you've done all the work previously, you kind of get a fresh start here. So it's a good thing. There we have it. Let's see how it could apply to other functions. Now, I'm just going to test the sequence of y values to see whether we have a linear or an exponential function or neither. Okay. Now we assume uniform changes in x, because if x doesn't change uniformly, you can't really test it. Okay. Now you could test it from a graph, and we'll probably look at that. But I'm going to actually look at your homework and make sure we're testing it correctly, or testing it in a way that you're actually going to need. We'll address other possibilities later. Okay, so anyhow, we test the y values, assuming uniform changes in x. So let's say the y values are, let me choose 243 81, 27, 9, 3, 1, 1/3. Okay, now it's fairly easy to see what the pattern is if you just look at the numbers from here down to here. You can see that every number divided by 3 gives you the next number. Okay, now, whether you see that 81 divided by 3 is 27 or 243 divided by 3 is 81, I wouldn't necessarily expect you to be able to do that. But if you look at these numbers, it should be pretty obvious if you know your basic arithmetic, okay? You shouldn't need a calculator with this one. Now, 81 over 243 is 1/3. 81 over 27 is 1/3. 27 over 9 is 1/3. 3 over 9 is 1/3. 1 divided by 1/3 is 1 times 3 over 1, which is 3. So we have the same ratio. And that's 1/3. Now, I didn't mention, if you would first maybe want to test this for linearity, but clearly there's a bigger change from 243 to 81 than there is from 3 to 1. So you can see immediately that the changes in these values are not all the same. Now, if you got numbers in several decimal places and stuff like that, it's not always as obvious, but you can still do the calculations. It doesn't matter what numbers I put here, you can divide them. And if they're numbers with 4 decimal places, you're perfectly within your rights to use a calculator to do the ratios, okay? If they're simple numbers, integers, simple fractions, then I really would kind of expect you to do the arithmetic, because people don't do arithmetic very well and need the reinforcement. And you understand it better if you do the arithmetic than if your calculator does the arithmetic. But only if the arithmetic is fairly straightforward for you. Okay, let's try another one. Okay, I got my. Let's just say you got this, and maybe they go on, but that'll be enough. Okay. The differences are 3, 5, uh-oh. I know what I did, and it's not what I intended to do, so I'm going to change some of these numbers. Okay, and now the differences are 3, 5, 7, 9, 11, and 13. Okay. I will notice, just tosses out there, it's not something you're necessarily responsible for right now, but you will be. And since I have the example up here, I'm going to make use of it. If I do the differences of these numbers, they're all the same. So I'm going to note what I call the second difference is uniform, which implies that the function is quadratic. So just incidentally, we have a test for quadratic functions as well as a test for linear and exponential functions. Okay. Now, if it's quadratic, it's not going to be exponential, but let's test exponential anyhow. The ratios are 11 over 8, 16 over 11, 23 over 16, 32 over 23, 43 over 32, 56 over 43. These are approximately equal to, that's 1.375. I'm just going to say about 1.4. This is 1 and 5/11. 11 goes into 5, 4, closer to 4. This is about 1.4. That shouldn't be. This should be less than this. I mean, this is 1.375. That's about 1.44 something. Shouldn't go up. And maybe it does. Maybe it does because it's not base from 0. Okay, anyhow, we'll get it. Okay, this will be 7/16, which is about 1.4. Now here we have 1 and 9 over 23. I'm going to need more decimal places to verify this. We're starting off with kind of a big number. This last one, 42 into 14 is about 1.3. 9 over 32 is about 1.3. This is about 1.4. Now, if you carry these out to more decimal places, you see that none of them are equal. Okay. We see these are not uniform, so this is not exponential. Although you would be kind of forgiven for thinking maybe this is exponential, just looking at it. But the test shows us that it's not uniform. Take it out to more decimal places, you'll see that none of these numbers are exactly the same. And of course, you can test that. Why are these two numbers not equal? It's because 11 times 11, which is 121, is different than 8 times 16, which is 128. Okay, and 16 times 16 is 256. 11 times 23 is 256. Oh, that can't be. Prime factorizations wouldn't work. 253, sorry. So anyhow, as you do these calculations, you can easily say that the ratios are not uniform, so it's not exponential. So if you were asked whether this is exponential or linear or neither, your answer would be neither. If you're asked whether this is exponential, quadratic, or linear, using this test, you would conclude that it's quadratic, and we're going to see that before too long. Okay. Now, what I want to emphasize is that this fits completely into our scheme of basic functions. And they're shifted and transformed and translated versions, okay? We have three of our basic functions right here: linear, quadratic, exponential. Tests for the other functions are a little more complicated, and we usually don't worry about them because in most applications, linear, quadratic, exponential are the big ones. Doesn't mean there aren't other possibilities. You go into different fields, and sines and cosines and stuff are important. There are tests for those, but those aren't even part of our first semester course. So we have this scheme. Okay. So that's quite a bit of time on the first problem, but it establishes that exponential, linear, and quadratic functions are in some sense different animals. The basic functions aren't the same, and neither are their transformed versions. They can't be. You cannot have a function that's both quadratic and exponential, or both quadratic and linear, and so forth. Okay. Now, there's another topic, another phenomenon that I find beyond belief that people come out of our schools not knowing, which is the idea of compound interest. Part of the curriculum in schools in this state and in most states in the United States includes some basic economic calculations, very practical, very important. And people, I don't know, I learned about compound interest when I was still in elementary school. And so did everybody else in my class. Some of them got it better than others, but most of us got it pretty quickly. It's not a difficult concept. Okay, so. Oh, gee, I don't like 10%. I'm going to say 12% interest. Compounded annually. This means add 12% to whatever your amount is every year. Okay, well, first year, what do we start with? What's our interest? And what do we end with? Put that first year down a little lower. We start with $1,000. Our interest is 12% of $1,000. Which is 120. So at the end, we have $1,120. So now in our second year, without going through the details of calculations, we start with $1,120. And I would put myself in a position where I got to do 12% of 1120, okay? But 12% of 20 is $2.40. Of 100 is $12. That's $14.40. And another 120, $114.40, yeah. And another 120 is 134. You know, I said what it was, and I think it's $134. Let's see again. Yeah, it's 12% of that is $2.40. 12% of that is 12. Yep, you got to have 40 there. Okay. So anyhow, we end up with them 1,254.20. In the third year, etc. Notice that we go up, that what we're adding each time is 120, then 134.40, and then 12% of whatever in the world this is. It's probably going to be something like about 150. Okay. You can verify for yourself that we have a common ratio. Which is 1.12. Now, $1.12 is 100% plus 12%, which equals 112%, which equals 1.12, expressing the percent as a decimal. Okay. 1.12 times 1,000 is 1 times 1,000 plus 0.12 times 1,000. Which of course is 1,000 plus 12% of 1,000. Meaning that we could get this same table this way. We can skip calculating the interest. We can say we start with $1,000, and let's put the year here, and we end with 1.12 times $1,000. Because multiplying by 1.12 is the same as adding 12%. In year 2, we have, and I'm not going to write out the numbers because they get a little hard to calculate, but we start with what we ended with here, and we multiply. And we end up with, well, 1.12 times this. 1.12 times this is 1.12 times 1.12 times 1,000. Clearly, we get 1.12 squared times 1,000. In the third year, we get 1.12 times 1.12 squared times 1,000, which we can see without going through all the details is 1.12 cubed. times 1,000. Every year, we multiply what we had in the previous year by 1.12, and we end up with 1.12 times our starting value, then 1.12 squared, because it multiplied by another 1.12 times 1,000, and then 1.12 cubed times 1,000, because we multiplied the 1.12 squared times 1,000 by 1.12. And clearly, this can go on to any number of years. So in n years, you're going to end up with 1.12 to the n times 1,000. There we have it. Okay, is the video working okay? Okay, good, good. Because mine is a little jumpy here. Okay. Well, let's now see what happens if we compound this same interest, compounded twice a year. Now, what this means is we don't give you 12% after 6 months and another 12% after another 6 months. Okay? We give you half of the 12% every 6 months. So now, following the procedure we did here, we're doing this at half-year intervals, so we have 1/2, 1, 3/2, 2, 5/2, 3, and so forth. We start with $1,000. We end up with 1.06 times $1,000. Then we start with 1.06 times $1,000, and we end with 1.06 squared times $1,000. Because, of course, we multiply this by 1.06. And we note that 1.06 squared is 1.1236. I'm sure you saw that immediately did that in your head, but just in case, there it is, okay? And you can check my calculations on that, okay? Simple squaring a binomial, but I'm not gonna go into that. Pretty easy to do that one. Now, 1.06 cubed times 1,000, you get into the binomial formula and stuff. And we should be covering that in this course, but apparently it's been dumbed down out of the curriculum and we don't. Okay, now, we then go 1.06 and we get 1.06 cubed times 1,000. And after 2 years, we have 1.06 to the 4th times 1,000. and so on, so that by the time we get down to n years, now notice that we don't have 1.06 to the n because we've multiplied by 1.06 twice for every year. Since we multiply by 1.06 twice for every year, we're going to have 1.06 to the 2n, because that's how many times we will have multiplied by 1.06 in n years. Now, I'm not even sure that your text develops this. I sort of fear that your text gives you a formula and allows you to use that formula without ever thinking through where that formula came from. I'm incapable of teaching a course that way. This is something that everybody should understand by the time they're 13 years old. At least everybody who might possibly be on a track to learn some mathematics, at least up to the level of pre-calculus, and preferably one course beyond that. And certainly anybody that wants to be an engineer or a chemist or a physicist or a mathematician should know this, so it doesn't get in their way later. Okay, well, this leads to the formula. Okay, so if you have an interest rate R, I'm getting in trouble. Because I'm using different letters than the book would. I naturally use N here. I'm going to change my N to an M, just so I can use N over here for the number of times you compound it. So now we don't have N over here, we have M. So I can use this. We compound N times per year. This means add I don't want to use 1 over n times, I just want to divide it. Means add this to the amount n times every year. Now I'm going to use T for the number of years, something I probably should have done down here. After T years, I said, I said add R over N in imitation of what I did here when it was clear what I meant. I say, man, R over N of the amount n times every year. Okay? Should use rather than 2. And implicitly, we're adding that to the amount. So after t years, how many times would we have added r over n of the amount? Well, we add it n times every year. So it's going to be nt times. In other words, if we're compounding it every month, that means we're adding it 12 times a year. So if our R is 12%, and we're adding 1/12 of that every month, 12 times a year, we're going to be adding 1% every time. And if R is 12%, then R over 12 would be 1%. So this just represents how much we're adding, just like the 1/2 of 12%, or 1/12 of 1% if we're doing it 12 times a year. In 5 years, if we're doing this 12 times a year, we would have done it 5 times 12 or 60 times. That's what our n times t is. It's the number of times we do it in t years. So if t is 5 and n is 12, meaning we're compounding 12 times every year, then that's going to be n times t, 12 times 5, 60 times. Okay, well, in any case, we'll have added this with the amount this many times. Each time we multiply by 1 plus r over n. So we get, if we're still doing the $1,000, but if we're not doing $1,000, it's whatever we start with, that's going to multiply by 1 plus r over n times t times. More generally, it's going to be, I'm going to use t sub 0 for whatever we start with. And we get this. And we'll call this P. Here's our general formula. Now I'm looking for an available board. That one's covered on both sides. This one's covered on both sides. Oh, wait, I still got a good one. I have a rough board behind there, but okay, so. We have, oh, I think just beep, there it's a, this formula. Now down here, I just called it P, but it's clearly a function of T. Okay, this is a function into which we can calculate, plug the number of years and see how much money we're going to have. assuming that the interest rate remains constant and so forth. It doesn't tell us what our money is going to be worth after 50 years. We don't know what inflation is going to be, but it tells us how much we have, and we could actually do inflation the same way if we had an estimate of inflation. Okay, P of t is this. This is an exponential function. This is our initial amount. R is the interest rate, and you've got to be careful. If it's 12%, that doesn't mean R is 12, R is 0.12. R is 12%, which means 12 per 100, which is 0.12. So R has to be expressed as a number, and you don't just take the thing in front of your percent and say that's your rate, okay? A common mistake, I don't think you'd make it, but it's easy to make, so I thought I'd warn you, okay? So you divide whatever your interest rate is by the number of times you compound per year, and that's this. And T is total number of times in T years. Let's say that R is 0.12 and N is 4. Then we get whatever our initial principal is. If you want to think $1,000, that's fine, but you can plug in whatever you start with. And you do this calculation. Well, that follows the formula, but we should understand where the formula comes from. So we understand that this is P naught times 1.03 to the 4t, meaning that we add we add 3%, and it's got to be 4 times per year. So what's P of 5? P of 5 is initial principal, which I'll leave unspecified, times 1.03 to the 4 times 5. In other words, P of t is this. T is 5, so we plug in 5 for t, and here we have it. Well, then this equals P naught times 1.03 to the 20th power. And I'm going to take a guess at what this is. This might be something like P naught times 2.1. 1.03 to the 20th should be about 2.1. and a question mark on that. I'm not totally sure of that, but 3% ought to double about 17 or 18 times. I'm sorry, ought to double in about 17 or 18 years. 20 years is just a little more than that, so a little more than double. I'd say it'd be around 2.1. I don't think it'll be as much as 2.2. But you could raise this. You can do this calculation, 1.03 to the 20th, on your calculator. You don't have to use mental arithmetic to do that. And even my mental arithmetic is not going to tell you to the nearest dollar. Okay? Just going to give you an estimate. Okay, this is an exponential function. Because I can write this as P naught times 1.03 to the 4t. Using the rules for exponents, raising something to the 4t is like raising it to the fourth and then raising that to the t. It's a multiplication rule for raising to a power. So it's like P naught times 1.13 to the t. Okay, well, you know what y equals a times 2 to the t is. A times 2 to the t is just your basic exponential function, vertically stretched by factor a. So that's one paradigm example, okay? Generally, it's y equals a times b to the t. Now you understand very well how we would construct a graph of just, without not worrying about the a right now, 3 to the t. We'd easily make a table for 3 to the t and graph it and everything would come out. We understand that. 1.13 to the t, well, you're not going to do that arithmetic in your head, but it's equally easy to graph, okay? So this is the general form of an exponential function. So I beat around the bush with all this stuff to get up to the general form of the exponential function, but it's important to understand that form. Let's see, do I have a back on this thing? I don't think so, nope. Okay, I gotta go to my rough board here, but we're almost done. So I'll just write big. Okay, so I'm using a lowercase a here because that's more consistent with the text. And the text actually uses x, I think, instead of t. But a whole lot of time when you do exponential functions, your variable's time. It's not x. But we'll go with a, b to the x. It doesn't matter whether you use x or t. X could stand for time. There's no reason it couldn't. Okay. If I want to graph this, it's really easy to graph it. I can start with my basic exponential function. And then I can put a scale on it. Looks like I'm almost out of, oh, there we go. So I'm going to scale this thing so it fits this, okay? This point will be 0, A. And then this point here will be 1, and the Y value here will have to be, well, the coordinates would have to be 1 and A times B. So now you've got a scale because, of course, here is A times B on the Y-axis. And here is A. So what's our value of B? Well, this is more than twice this, isn't it? This is A times B, and this is A. So B has to be more than 2 because 2 times this is only this big. Okay? So for this graph, let's say B is approximately 2.3 because this is about 2.3 times as far from the x-axis as this is. Now my point is the graph will have exactly the same shape as the 2 to the x graph, but it's going to have slightly different coordinates. That's the last thing I'll do. I don't have much board space, so it isn't going to take us much longer. So we've got 4 equals, y equals 4 times 1.7 to the x. We could start out with our basic exponential graph, and I'm not going to attempt to draw it really accurately. I'm just going to kind of look at this and try to do it about the same. Then if x equals 0, clearly 1.7 to the 0 is 4. So now this point has to be for y equals 4. Then if x equals 1, y is 4 times 1.7, which is 6.8. Now 1.7 times 4, if this is 4, well, we can put a scale on this. Okay, we've already got our y scale. So there's 4. Double that, we've got 8. Double that, we've got 16. So here would be 12. Okay. If x equals 1, you can easily see that y is 6.8. And 6.8 is between 4 and 8, pretty close to 8. So here is y equals 6.8. meaning that this has got to be 1. Because when x is 1, y has to be 6.8, meaning that the point on this graph where y equals 6.8, which is right here, has to have x coordinate 1. And now we've taken our 2 to the x graph and we've made it into 4 times 1.7 to the x without really doing much work. Okay, well, it's actually a fair amount to think about, but none of this is particularly difficult, and I hope this will be helpful to you on the homework. And if you run into things that you don't understand well, let me just take a quick look. I think you're going to be just fine on this. And this assignment is just a lot of examples. Okay. What we did for compound interest works the same for an unrestricted population growth. I've got a tank full of little fish and start with a couple of little fish. After a while, I'll have twice as many little fish. And then after the same amount of time, I'll have 4 times as many. And after the same amount of time, I'll have 8 times as many. And then 16 and 32, 64, 128, et cetera. Okay? Same thing. Your fish grow at a certain rate per unit of time. Your formula can equally well apply to fish. Okay? In ways that aren't totally analogous to what you do with compound interest, but give you the same kind of function. So if P stands for population, okay, this is a population that increases by 3% 4 times a year. And that's realistic for, rabbits or something, okay? For creatures that reproduce quickly, that reach sexual maturity quickly, that could be a perfectly realistic model. Now, after a while, they fill up the available space or eat up all the available food, or they become more available to predators, and the example doesn't work anymore, but that's just another paradigm example. And then you have radioactive elements decaying, and you'll understand that, I believe, when you read it, if you understand what we've talked about here. Okay? Okay, so enjoyed seeing you today. Haven't seen many students. Matter of fact, you're the first one I've actually seen. And well, my first class didn't show up. In my second class, I had the person in class many times, but due to where he works and stuff, he asked to attend from work, and he can't be showing me pictures of what's going on at work. I'm not sure what goes on there, but it's an engineering company, so it's nothing that we really have to worry about. Probably, they don't want people to see their patented processes. So I didn't get to see him, but of course I know him well. So I'm glad to see you. I saw at least one student today. I have plenty to do with other students. I'm just not going to be able to see them. Okay, well, you do well. Do you have any questions at this point?
No questions. Just the assignments will be in the open math and on the assignment page, or just the open?
Yeah, I don't think you have anything on the assignments page for today.
Okay, sounds good. Okay. Thank
Probably
you.
something next time, but just get into chapter 4.
Will do. Thank you.
Thank you. Bye-bye.
Bye-bye.